In 1982, there was one SAT question that every single student got wrong. Here it is. In the figure above, the radius of circle A is 1/3 the radius of circle B. Starting from the position shown in the figure, circle A rolls around circle B. At the end of how many revolutions of circle A will the center of the circle first reach its starting point? Is it A, 3/2, B, 3, C, 6, D, 9/2, or E, 9? SAT questions are designed to be quick. This exam gave students 30 minutes to solve 25 problems, so about a minute each. So feel free to pause the video here and try to solve it. What is your answer? I'll tell you right now that option B, or 3, is not correct.
Oops, sound glitch. Where am I at? Am I on? I think I'm on. Hope I'm on. Hope we're recording. Hi boys and girls, it's me Butch. My name is Terry David Silvercloud. I'm not native, just sounds that way. I'm 79 years old. I'm a photographer and artist, and I have a passion for theoretical physics and motion physics. And a couple of weeks ago, I came across Veritasium's video about the SAT question that everybody got wrong, except for 3 students who protested the question. And I thought it was such a fantastic question that I would try to give a short answer. So I know I'm a yacker, I go on and on like a dripping tap. I'm going to give you a fast, quick explanation of the answer and the how and why. I think it's just such a good question that should be taught at the basic geometry level. It just should be thrown at all students to think about this one, and certainly for engineers to make them just think when they get back into studying ratios of gears and stuff. So without further ado, because I do go on and on and on, I hope that's going to show up. I hopes. So when the question was posed, the question mentioned you are measuring from the center of the circles. So that's important to remember, that the center of the circle. You got so distracted by the simple ratios that you were thinking, oh, that's simple. 3, 1, 3, it's got to be 3. The answer is 4. So the diameter of the small circle is 2. 1 plus 1 is 2. Its circumference is pi times 2, or 2 pi r. So we're just not going to think about the pi part. We'll just remember the 2 part. And this is the big circle, and its radius is 3. So it'd be 2 pi r would be 6, or 2 pi d would still be 6. So the diameter of this big circle is 6, and of this one it's 2. But what we're interested in here is the path that this circle is going to follow. And since we're measuring from the center, the path that we have to pay attention to, that nobody seems to be paying attention to, because you thought it was such an easy question, is this path. It's a path outside of the main circle, not on it, and not out there either, even though the outer edge is following that circumference. The actual path is measured from the center. So what we need to know is the diameter or radius of this circle here to the center. So it's going to be, the radius will be 3 plus 1. Or if you want to use the diameter, sorry, I'm going to lose myself. we want to know the circumference of this, so it's 3 plus 4. That's the radius here. Where's the guy? A ruler here. Here, the radius here is 3 plus 1, which is 4. And the diameter twice would be 8. So the diameter of that big circle out here that this is going around is 8. And the diameter of this one is 2. And you're back to the diameter of this one. The point is you can divide 2 into 8 and you get 4. In other words, you can put 4 of these things in complete turns. I hope that made sense. The math made sense, sort of. I wanted to make sure I covered everything, and I'm not sure I did. Here's a different drawing, just to quickly review it, what you got to pay attention to. The radius of the small circle is 1, the diameter is 2, and the path, the invisible path that you must measure, is from the center of the small circle as it circles the large circle until it gets back to here. And you need to know the radius of that circle there. And the radius is 3 plus 1 to the middle of the circle, which is 4. So it's a diameter of 8 for that big circle out there, this circle from here over to here. And the outer circle you don't care about because it's not part of your measurement, because you're only worried about the center. And it turns out that that point, and that point, when they're all in line, mean that they all lined up in line at the same time. And it did it because this outer point here is traveling much, much, much faster than this one, and that one's traveling much faster than that one. It means that the energy of this turning circle being generated by this turning circle would really be concentrated right there, which is a good place to have your saw going, or in this case, if you're running a drive shaft through the center of this thing. This whole thing leads itself to how you think about gears and pulleys and how you can distribute energy. So like I said, I go on and on and on like a dripping tap, and I have. All you need to do is remember that you need to know this radius that the little ball follows. That's all you need to know. And so I think that's it from Butchy Poo. I do go on and on like a dripping tap. And I see, well, it'd be a good camera. Two. Where's 2? Hi 2. So Butchy Poo's going to shut up and hope I covered it all and that it sort of kind of made sense. And I gotta look at my buttons here. I'm going to say bye-bye.